When you look at your phone to unlock it, or scroll through a streaming app that seems to know exactly what movie you want to watch next, it feels like there is a thinking brain behind the glass. A computer possesses no inherent thoughts. It is a collection of silicon and copper activated by raw electrical energy. Calculating machines once relied on physical gears and cranks to solve equations. As engineers moved towards electrical systems, those mechanical movements were replaced by physical switches, locked into one of two states, on or off. The intelligence we experience is a result of billions of these microscopic switches, flicking on and off millions of times a second. In the late 1930s, physicist John Vincent Adanasoff realized that electricity could compute using base 2 numbers, a binary system of ones and zeros that mirrored the behavior of an electrical switch. At the same time, mathematician Claude Shannon discovered that these electrical switches behaved exactly like a forgotten logic system from the 1800s. That system was Boolean Algebra. Its creator, George Boole, designed the math to map human logic using only two values, true and false, or, as a computer reads them, 1 and 0. Boolean algebra provided the mathematical translation layer required to turn abstract human ideas into physical electrical signals. This truth table for the AND operator acts as a gatekeeper. Like a banking login requiring a password and two-factor code, both inputs must be true. If either input is 0, false, the final output is immediately forced to 0. The OR operator is a broader net. When filtering shoes by size 10 or 11, a result shows if either condition is met. A 1 in any input column mathematically guarantees a 1 in the final output. Then there is the NOT operator. It is an inverter that flips a 1 to a 0, or a true to a false, the logic used to filter messages marked as spam. Every app feature, search result, and digital filter is constructed from these three logic gates. To make complex decisions, these operators must scale. Consider an airplane autopilot that relies on three separate sensors reading the altitude. To ensure safety, the system takes a majority vote. This table represents that majority function. The system outputs a 1 only if two of the three sensors agree. Engineers program this using the sum of products method, looking at the table in reverse to find every scenario outputting a 1. That first scenario translates into a string of ANDed variables, not x and y and z. By adding all the successful scenarios together with OR operators, we create a single expression representing the entire decision-making process. Even life-critical algorithmic decisions reduce to a mathematical formula of ANDs and ORs. There is a direct link between this math and the physical world. In computer engineering, every term in a Boolean equation must be manufactured as hardware. A long, unoptimized equation requires unnecessary wires and wasted transistors, resulting in a large, expensive circuit board. Engineers use the rules shown in this table, called Boolean identities, to compress the equation down to its simplest possible form before it is built. Crossing out a redundant variable on a page deletes a physical wire from the design. By minimizing the math, you shrink the hardware. Every single screen tap you make sends electricity racing through a microscopic physical maze, fully optimized by 19th century logic.